Hi folks, this is Mr. S, and this lesson is on spontaneity, which is part of HL energetics. A spontaneous process is one that occurs without outside intervention, so it pretty much happens on its own. Let's take a look at an example where we have a spontaneous and a non-spontaneous process. So here we see that the ball is going to roll down spontaneously, and the ball does not roll up spontaneously. So it's non-spontaneous. So the question now becomes, what is making this ball roll down on its own? Well, you might come up with the fact that there's gravity pulling it down. You might also come up with the fact that there's this hill is at an angle. More importantly, however, is that you'll see that this ball has stored energy, or it has potential energy. And typically with processes that are spontaneous, you will see that there is a store of potential energy, and as the reaction proceeds, spontaneously, you will see that there's a decrease in energy until it reaches a value of 0, and at that point, the reaction tends to cease being spontaneous. Now, this is not physics, this is chemistry, so I'm interested in taking a look at a chemical reaction and stating if that reaction is going to be spontaneous or not. In this particular case here, I see that this is a decomposition reaction. My enthalpy change is negative, which means this reaction is exothermic. I see here that I'm going from solid calcium carbonate to solid calcium oxide, and then I'm also forming carbon dioxide. So how can I tell whether this reaction is going to be spontaneous or not? Well, let's take a closer look. There are two driving forces that cause a reaction to be spontaneous or not. And one of them is change in enthalpy. Well, change in enthalpy we have seen when we did energetics. Change in enthalpy is represented as delta H. Now, delta H can be negative, or your delta H can be positive. If your delta H is negative, we are dealing with an exothermic reaction. When the delta H is positive, we are dealing with an endothermic reaction. And the second factor is change in entropy. Now, entropy is something that you probably have not heard about. The symbol for entropy is S. But we are specifically interested in change in entropy, which is represented by delta S. Now, delta S, like delta H, can be positive or it can be negative. So let's take a closer look at how these affect spontaneity of chemical reactions. When we take a look at enthalpy change, I've written here that exothermic reactions tend to be more spontaneous. Let's take a closer look. When I take a look at an exothermic reaction here, you can see my reactants have more energy than my product. Well, earlier when we mentioned the example of the ball, there was more stored energy. So if I have a situation like this where my reactants are going from high energy to low energy, this reaction tends to be more spontaneous. And that energy difference between them is lost to the surroundings. We learned this when we were talking about energetics. The second thing that you should keep in mind is that the activation energy for this reaction is much lower than the activation energy for an endothermic reaction. Bottom line, exothermic reactions tend to be more spontaneous. So here's what we can conclude. A decrease in enthalpy, in other words, your negative delta H, is favored for spontaneity. Let's take a look at entropy. Now, entropy is defined as a measure of randomness. That is not the actual definition, but for our purposes in high school, that's good enough. Here, you can see that I'm going from ice to water. As you can see here, the molecules are more random. In other words, they have more freedom to move about. And here, the molecules are specifically the water molecules, are kind of stuck in this position. So what I'm doing is I'm going from ice to water. Here I have more order, and here I have more disorder. So what I've done is from left to right, I've actually increased my disorder. Now, you can imagine that if I go from liquid to gas, water vapor, I'm actually going to increase that disorder even more. So what chemists have noticed, or physicists have noticed, is that when the entropy change, in this case, in the case of going from ice to water to gas, my entropy change is, as a matter of fact, increasing, which is represented by delta S. When my delta S is greater than 0, which is the same as saying positive S, my reaction tends to be spontaneous. So, in order for you to apply the concept of entropy to chemical reactions, you need to know if their entropy is increasing or decreasing in an actual chemical reaction. So if I'm looking at this reaction number 1, you see how calcium carbonate is going to calcium oxide and carbon dioxide. I am going from a solid to a solid and a gas. I can tell that I have more order here and I have higher disorder here. Because I've gone from order to disorder, my entropy here is increasing. Well, that is something that is favored for spontaneity. If you take a look at my second reaction here, I have 4 moles of gas on the left and I have 2 moles of gas on the left. So I have more disorder here and I have more order here. What I'm doing here is I'm actually making the system more ordered, which means I am decreasing my entropy. If you take a look at this third one, here I'm going from two aqueous solutions into a solution and a solid. Because a solid has lower entropy, in other words, it has more order, I am once again decreasing my entropy from left to right. And lastly, when you take a look at this here I have 2 moles of gas, and on the right side I also have 2 moles of gas. So here your delta S is actually equal to 0. There's no change. So here's what we've noticed, an increase in entropy. So if you have a positive delta S, that is favored for spontaneity. Now, based on what we just learned, I can now conclude that if my enthalpy change is negative and my delta S is positive, the reaction is going to be spontaneous at all temperatures. And also now, if I know this, I know that if my enthalpy change is positive, which means the reaction is endothermic, and if my delta S is negative, which means my entropy is decreasing, my reaction is going to be non-spontaneous. Now, this brings up a big question. What if those two signs were the same? What if my delta H is negative, which means this likes spontaneity, and when my delta S is negative, this doesn't like spontaneity? And my delta H is positive, this doesn't like spontaneity, but delta S does like spontaneity. So in this case, these guys are kind of fighting against each other. So what happens here? Temperature decides spontaneity. All right, to solve this problem once and for all, we take a look at this equation, which is known as the Gibbs free energy. Now, Josiah Willard Gibbs was a physicist that did quite a bit of work in this area, and he gave us this equation, and I would strongly suggest that you memorize this equation. Now, we can take a look at delta G as our final decider of spontaneity. Delta G can be negative, delta G can be positive, or delta G can equal 0. If delta G is negative, the reaction is always spontaneous. What I mean by always is that at all temperatures. If delta G is positive, it is non-spontaneous, regardless of temperature. And if your delta G is equal to 0, here, the reaction is said to be at equilibrium. So, what kind of questions can you be asked here with this? Well, you can be given the value of delta H, delta S in temperature, and you can be asked to find delta G and discuss the spontaneity of the reaction. If delta G turns out to be negative, then that means the reaction is going to be spontaneous. If you solve this and delta G is positive, then you can say, oh, the reaction is not spontaneous. So, the other question you will be asked will be, what values of delta H and delta S will make delta G negative or positive or equal to 0. So there are 4 scenarios that you should be aware of. So if I want delta G to be negative, right? If this reaction is going to be spontaneous at all temperatures, we just learned this, my delta H must be negative and my delta S must be positive. So you see here, if I'm solving that equation, if my delta S is positive, this term is negative, the T delta S term is negative, and my delta H is negative. So you can see that the final answer to this would be a negative value of delta G. So we learned this. If my delta H is negative, that's an exothermic reaction, and my delta S is positive, my entropy is increasing. Both of those are favored for spontaneity. Now, we also learned that if my delta H is positive, which means the reaction is endothermic, and my delta S is negative, which means my entropy is decreasing, both of these are not favored for spontaneity. And if I just apply some little bit of math here, negative times negative will make this entire T delta S positive, and my delta H is also positive. What that ends up doing is it makes my delta G positive. I don't have room here, so I'm going to write the delta G value here. So these two situations are pretty clear cut. Now, on my last slide, I said that when the signs of these are exactly the same, so if I have a positive, positive, and negative, negative, again, these signs that I'm putting in are for delta S and delta H. I haven't talked about temperature yet. We said that when these two signs are the same, that is when temperature decides spontaneity. Well, let's take a look. So if my entropy change is positive, that means this is good because my entropy is increasing, but my enthalpy change is positive here. What kind of temperature do I want? Well, this reaction will be spontaneous at higher temperatures. And why is that? Well, because if my my temperature is high, my T delta S, which is negative T delta S, becomes bigger. If my T delta S is bigger than delta H, that is going to make my delta G negative. And if my delta G becomes negative, then the reaction becomes spontaneous. So what I would say here is if the two signs are positive, my delta S is positive and my delta H is positive here, the reaction will become spontaneous as I increase the temperature on it. And lastly, if my two values are negative, so if my delta H is negative, that's an exothermic reaction. If my entropy is decreasing, here, what I want to do is I want to make sure my delta H is bigger than my negative T delta S. So in order for me to do that, I need a low temperature. So this one here, this reaction will be spontaneous at low temperatures. Why? Because I want this term, which is my delta H, to be greater than my T delta S. And in order for that to happen, that temperature has to be low so that this term, which is going to be positive, this term is smaller than my delta H, and my negative sign of delta H would win, and that would cause my delta G to be negative. If you're an IB, there are a lot of questions asked about this. So once again, the final decider of spontaneity is delta G. If your delta G turns out to be negative, the reaction is spontaneous. If it is positive, the reaction is non-spontaneous. And if delta G is equal to 0, the reaction is at equilibrium. So here's a quick summary of what I just said. All right, so what can we conclude about the spontaneity of this reaction? I'm taking a look at this reaction. This is exothermic. We know that's favored for spontaneity. Here, I'm taking a look at my entropy, and you can see here that I'm going from 3 moles of gas to 2 moles of water. So what I'm doing here is actually I'm decreasing my entropy, which means my delta S is negative. So if I'm looking at this equation, delta G equals delta H minus T delta S, this is negative, and this is also negative. Well, what's going to happen is my T delta S, because of the negative and negative, is going to become positive. Now, what I want is, if I want delta G to be negative, I want my T to be a lower temperature, because I want my delta H to be bigger so that that negative sign here beats the positive sign and my delta G becomes negative. So this reaction would be spontaneous at lower temperatures. And lastly, a quick note on spontaneity and equilibrium. So we learned about the concept of equilibrium. We learned that some reactions go to completion, and we learned that some reactions reach equilibrium. So what causes this? Well, what causes this? If A goes to B and this reaction goes to completion, this means that the forward reaction is spontaneous. Whenever you have a forward reaction that is spontaneous, that reaction either tends to go to completion or it reaches equilibrium late. Now, when the case of a reaction that reaches equilibrium, now we have two reactions that are fighting against each other, and these two reactions are somewhat spontaneous, both of them. So you will see that if your equilibrium is established early, we have a situation where our reverse reaction tends to be more spontaneous. That's why B wants to go back and form A. If my equilibrium is established late, you can see here, so this is the timeline of the reaction. That's the start and the end of the reaction. And this would be early equilibrium. If my equilibrium is established late, that means that my forward reaction here was more spontaneous. So you will see that when we're dealing with equilibrium reactions, we have two reactions that have varying degrees of spontaneity. But if a reaction goes to completion, it is definitely spontaneous in one direction. Now, one of the things you will learn in HL equilibrium is that in order for us to decide, quantify this position of equilibrium to see whether it's early or late, we take a look at something called the standard Gibbs free energy, which is delta G naught. So you will get a graph that looks like this. This is the graph of delta G naught. Here you can see that there's my delta G naught, which is the basically standard Gibbs free energy here. My standard Gibbs free energy, which is the difference between the Gibbs free energy of the reactants and products. And again, it's products minus reactants. That's what I'm getting this delta G from. And here, there's my reactants, there's my products. Products minus reactants here will give me a number that's bigger than 0. And here, my reactants and products basically have equal Gibbs free energy, and my delta G is equal to 0. The important thing to remember about this particular graph here when you're doing equilibrium is to look at the valley at the bottom of this valley. So if I'm looking at the bottom of this valley here, notice here it says reaction progress. This bottom here is actually extent of reaction, or position of equilibrium. So what I mean by that is the farther away from 0 the valley is, the later equilibrium was established. If this valley the bottom of the valley here is closer to 0, then this one, equilibrium, was established early. And if the valley is right in the middle, here we say that k is equal to 1, equilibrium was established in the middle. Now, if that doesn't make sense to you, you can take a look at the lesson on equilibrium. Hopefully that helped. Please subscribe for more videos.